Buenas tardes, sean todos muy bienvenidos a la Universidad Paraguayo-Alemana para esta transmisión en que, un momentito, acá, pues, perdón por el fallo. Buenas tardes a todos, sean muy bienvenidos a la Universidad Paraguayo-Alemana. Es un gusto tenerlos acá con nosotros. Muy bienvenidos a aquellos que se conectan desde otros puntos de Paraguay, de otros países. Un saludo especial a la comunidad de la UPA. Y yo soy Marcelo Cartier, profesor de Ingeniería Industrial. Voy a ser el moderador de este webinar, junto con mis colegas Verónica Rojas y Joel Prieto. Buenas tardes, Verónica.
Buenas tardes, profesor Castier. Estamos muy contentos de poder apoyar la moderación de la charla.
Buenas tardes, Joel.
Buenas tardes. Aquí en la segunda charla de este ciclo de webinars. Estaremos atentos.
Y seguimos atentos. Entonces, hoy, como en los seminarios, los webinars anteriores, se transmite por Facebook y, por supuesto, esperamos que ustedes nos manden comentarios, nos manden preguntas para que después de la presentación tengamos una sesión muy dinámica con mucha interactividad. En este momento yo voy a pasar a hablar en inglés porque nuestro invitado no habla castellano. Entonces, good afternoon to all of you. Good afternoon to our guest, Professor Joseph Boutros, who is connecting from Paris, France today. Professor Boutros got his master's and PhD degrees from the National School of Telecommunications in Paris. He worked there for about 10 years as associate professor. Since 2007, he is a professor of electrical engineering of Texas A&M University at Qatar. Professor Boutros is a specialist and expert in the integrity and privacy of information sent through by means of telecommunications. And privacy is exactly the topic of today's presentation. He is a consultant and collaborator with a number of important international companies such as Alcatel, Philips, Nokia, Bell Labs, Google. So he has a tremendous experience. He has more than 250 papers, cited more than 7,500 times. So really impressive career, really impressive numbers. It's a great honor to have you with us, Joseph. Please be welcome, even if virtually, to UPA, and we look forward to your seminar this afternoon here, this evening in Paris.
Thank you, Professor Castier, and buenas tardes, Paraguay, après-midi au Paraguay. Sorry for not being able to make the presentation in Spanish. I'll start sharing my screen, and then I'll start through my slides. Okay, so this is a talk. It has, let's say, it has a lot of mathematics behind, but I tried to make a talk open for public. So for engineers, for students, for mathematicians, for computer scientists in public outside university who would like to discover how cryptography is working. And you will see, in fact, in the first main part of my presentation, I will show you that cryptography, of course, every day you are using, all of you are using cryptography without knowing about it. But cryptography is very old topic. So currently, as Professor Castier said, I'm a professor of electrical and computer engineering at Texas A&M University at Qatar, and making this presentation from Paris, France. So let me show you first how cryptography is within the field of other area of sciences. And you notice this picture, I had fun making this picture 4 weeks ago. And it's more or less similar, like very similar to a triangle. You can see that mathematics is everywhere. So all corners, you can see mathematics in all corners. So let's say mathematics, of course, computer science without mathematics, and cryptography can, many people consider cryptography as part of computer science. But you have also a main field, which is information theory, part of it applied in cryptography. Information theory can be seen as, mathematically speaking, as the child of probability. And as you know, probability is the child of measure theory. And then with number theory, of course, number theory directly going to cryptography from mathematics. We out of number theory, as today during my talk, algebra. And from algebra, there is a field called coding theory, error correcting codes. So here the word coding doesn't mean programming, it's error correcting codes. And cryptography is also, it uses tools from coding theory. And more recently, quantum mechanics to do what we call, post-quantum cryptography doesn't need necessarily quantum mechanics, but we need to understand how a quantum computer is working and do quantum computer to let run the post-quantum cryptography. I will talk about it just at the end of my talk before the conclusions. So let's say what are the most important here sciences supporting cryptography: number theory, computer science. These two, and then maybe in the second, coding theory and probability. Now, I would like to introduce some vocabulary. That's why I'm showing you now one of the simplest models for cryptography. And this is very standard in cryptography. Alice is the transmitter. So Alice would like to send a message to Bob. Bob is the legitimate receiver. So Bob would like to get the message from Alice. And then you have between Alice and Bob a communication channel. And who's listening there is Bob. And unfortunately, we use also the name Eve for spy. So the spy is also called eavesdropper in English. So we have Eve listening to Alice and Bob, and Alice has a text. And the text in normal language, we call it a plain text. And of course, Bob would like to have a copy of this plain text. So we cannot send, Alice cannot send the text as it is because Eve will get a copy, of course. So what do? We need to encrypt, but here what I showed just for fun, I put two ladies listening, two Eves, because you may have many spies, in fact, around you, not only one spy. So the idea is the following. Alice will do some function called encryption to convert the plain text into a text which cannot be understood by Eve. We call it ciphertext. So the ciphertext is the text which cannot be understood by Eve. This is after encryption. How Alice is doing this? She's using a key, some secret key. You can call it a password if you would like, but in cryptography, we call it a key. And this key is the same as the one, as you can see in my picture, the one used by Bob here in this picture. So what happens, the ciphertext will go through the channel. Eve, the spy, is listening to the channel. It can be the internet, it can be wireless channel, it can be cable channel, whatever. It's not important. Mathematically, here, this is true for any physical channel, okay? So please get a copy of the ciphertext after encryption, not before encryption. Eve cannot understand what's happening, and Eve does not have the key to be able to decrypt. Decrypt is the inverse operation. But Bob has this key, and Bob is going to decrypt, and then Bob is going to get the plain text. Now, of course, some of the question you may ask, but how comes that Bob is getting the same key? If Bob's the phone talks to Alice, please send the key, but it can be listening to the phone, okay? This is before they invent smartphones. So now on a smartphone, imagine you are using WhatsApp or FaceTime or whatever, and you are talking to Alice, it's the same. Someone can, if the communication is not encrypted, someone can listen to you. Now, of course, I will mention this later in my talk. WhatsApp is encrypting end to end, but not all applications are encrypting the communications, or audio or video or whatever, or data. Okay, so this is the simple model for, please remember this model. Alice is the legitimate transmitter, Bob is the legitimate receiver. E is the spy, and we encrypt, decrypt to convert a plain text into ciphertext. And now I'm going to summarize, introduce a little bit more vocabulary for you. So what does it mean, cryptography? This word comes from Greek. It means, graphy means the end is writing, and the crypto means in Greek means hidden or secret writing. So this is the meaning of cryptography. Now, when we encrypt, this is the word I used already in my picture between Alice and Bob. When we encrypt, we make the plain text become a secret. Okay, so make the writing secret. Now we have two other verbs, synonym encrypt. Okay, scientifically speaking, we can say encode. So we can say Alice is encoding the plain text in ciphertext. Some people also use in cipher. In cipher is the same word as it. Okay. Now, the message itself, the message before encryption, plain text or normal language. After encryption, ciphertext, we can also call it a code. We can also call it a cipher with the text after encryption. Now, the operation made by Bob, the opposite. It can be called decipher, it can be decode, the opposite of encoding, and be called decrypt, the opposite of encryption. So this is converting the cipher text into a text in normal language, in plain text. Okay. Now notice we have cipher appearing again in the middle of the table. Oh, here. Why cipher is appearing again? Because it's not a verb, it's not related to cipher. Huh? Here it's related to a set of all algorithms for encryption and decryption. Okay. Now, if I add to these algorithm, encryption of decryption, I add a third type of algorithm for exchanging the key between Alice and Bob. We call this a crypto system. So crypto system is more general than the cipher. It has key exchange. It means the secret between Alice and Bob. There should be some algorithm to exchange the secret, and the secret key, the key is used to do encryption and decryption. Okay, so this is called cryptum, but that's fine. I mean, what I want, this is a table you don't need to now during my talk to understand all these names. I think the most important is encryption, decryption, ciphertext, and plain text. Plain text is the normal language. Ciphertext is the one that we do not understand. Now, cryptanalysis is something else, because usually what scientists are doing and cryptographers are doing, they want to make algorithm to attack an encryption standard. Why? To see if it is secure or not. And algorithm for attacking, for breaching cryptography are called cryptanalysis. And now cryptology, the last row in my line here, in my table, this is the science grouping everything. Grouping cryptography. Cryptography means key exchange, encryption, decryption, and the attacks, and the cryptanalysis. So this is cryptology. So this is much more general. Now, again, I want you to remember during my talk, 4 words, it's more than enough from this table. Encrypt, decrypt, plain text, ciphertext. And please remember, is transmitting to Bob. Alice is doing the encryption, Bob is doing the decryption, but sometimes we will do something weird. We wear the roles. Okay? And Eve is the spy. Fine. So let's quickly see how this word appeared. It's very funny, because I made this similar talk in Qatar. And then a colleague in France, he told me about, why not you should talk about the word cipher, because the word is from Arabic, and it's the word al-sifr, means zero, le zéro. So it seems it went from Arabic, the word cipher, to medieval Latin, to French, and then it went to English as cipher. In French, we say le chiffre. And encryption in French, it's chiffrement. So it's a very similar word, cipher to cipher. So chiffrement, déchiffrement for decryption, which is more or less the same as in English, Now, why we are using the word cipher for encoding and for encryption? I gave here two reasons, two historical reasons. Because, of course, encoding involves numbers. And what happened a long time ago, hundreds of years ago, I mean, even if you go to the Roman era 2,000 years ago, in Europe, they didn't have the zero. And this was very annoying for people. Not have the zero in the counting system was very annoying. Okay, so one of the reasons I cited, the second one, is the absence of the zero in the Roman number system. And so people started using cipher for encoding and encryption. Now, more historical references I put here, the first one and the second for the history of cryptography. The third reference I put, the one by Claude Shannon. This is a very long article. This is 60 pages. He wrote when he was at Bell Labs in New Jersey, in the United States. And this is more or less how to combine information theory and cryptography. And he gave very original ideas in this document. I will cite two of them about confusion and diffusion properties. Okay, so if you need, maybe Professor Castier or Professor Veronica Rojas can give you the copy of the slides, but you can also send me an email. Okay, so before going into the key exchange, asymmetric cryptography and symmetric cryptography, you can follow my talk on the top in the slides. You can see the bullet moving, and right now I am in the first bullet in the history section. I'm going to show you now some historical review about cryptography. This is called classic cryptography. It's from ancient times, 4,000 years ago up to now. It's a weak cryptography. People were using unknown symbols. People sometimes were permuting the letters or substituting the letter. Now, substitution can be done also by a permutation of the alphabet. Okay, and one excellent book is the book by David Kahn, 1996. This is really an excellent book for the history of secret communications. And indeed, it started a long time ago. So this is almost 4,000 years ago, 1900 BC in Egypt. During the reign of two pharaoh, the two kings, Amenemhat is very known, Amenemhat II and Sesostris II. So this is during the Middle Kingdom in ancient Egypt. And it seems that a scribe was writing some non-standard hieroglyphs time. And this was found in Egypt in Beni Hassan. Beni Hassan, this is a village in Egypt. But the tomb was not the tomb of a king. The tomb was the king, great chief. And the name, I put the name here, the name is Khnum-Hotep II. So this is the name of this chief. And in his tomb, you can see the non-standard hieroglyphs. So people suppose that this was one of the early encryption in that time. Now, of course, some are saying that this is probably just for enjoyment. This is just enjoyment for the intellectual members of the community. Why? Because at that time, people were not all capable of reading and writing. Only the elite, they knew about writing and reading. Yeah. So the picture, the Sphinx I put on the left here, this is the Sphinx of the king at the time. Amenemhat II. It can be, if you visit Paris, you're welcome. This is in the Louvre Museum. And then the wall painting you see on the right, this is in Egypt, in Beni Hassan. This is tomb number 3. And this is the picture of this great Egyptian chief. He's hunting birds in the picture. So really 4,000 years old. Now, I'm talking about Mesopotamia, the old Iraq. And probably some of you knew about cuneiform writing. Again, this is not alphabet yet, because the hieroglyphs is not alphabet. Cuneiform is not alphabet. Cuneiform than hieroglyphs. It seems that people working in cryptography, they found some traces of cryptography later, after Egypt, in 1500 BC. So it was 1900 for Egypt. This is 1500 BC. And what they found a craftsman's recipe for pottery glaze, okay, in old Mesopotamia. And it was written in cuneiform. Yeah. So here I put just a picture of how the cuneiform writing was progressing, was being modified from the Sumerian up to Babylonian up to Assyrian. Okay. Now, this is another example, but this is a little bit later. This is only 600 to 500 BC, but this is one of the true examples of cryptography. This is called Atbash, used by the Hebrew, and it was using not Latin alphabet, it was used with the Hebrew alphabet. So what was the idea is to read the alphabet backward. So the A becomes Z, the B becomes Y, the C becomes X, and so on. Okay, you flip the alphabet. And that's why the Atbash cipher, it's called the mirror code also. And if you read the book of Jeremiah, it seems that the Hebrew, they encrypted, so this is 600 BC, they encrypted the word Babylon as Sheshek and the word Chaldeans as Levkemai. Okay, and of course you can cut the table into two and just choose half of the table. Just 13 letters. You put 13 letters on the top, 13 letters down. So A becomes Z, Z becomes A, and so on. M becomes N, N becomes O, and this is how they. Of course, this is a very weak cryptography. I mean, nowadays you cannot do something like this just for a game. Yes, why not between children? Yeah. So let me show you a little bit more advanced way of cryptography. This is invented by the Greeks. The name, now be careful, the name is very weird to be pronounced in English. So this is 400 BC, 400 before Christ. In English, you pronounce this word very similar to Italy. Okay, Italy. So you say skittily, this skittily. In French, we call it le bâton de Plutarque. Plutarque was a Greek philosopher. So the idea is to take a baton, a rod, and then you take a strip, and then you wrap the strip around the rod, and then you write, and then you unwrap, you unfold. When you unfold, you cannot read anymore what you have. So you need to read the text. You need to fold again on the same rod, but or another rod with the same diameter. So the key here, the encryption and the decryption key or the password, is the diameter of the cylinder. If you change the diameter, you don't understand well when you read. So let me show you an experiment I did here at home 4 weeks. Of course, I didn't have a wood. I took a cartoon rod cylinder and then cut paper. I made of paper. Then you notice I wrapped the paper around the cartoon, and then I wrote. So I didn't put spaces. So notice I wrote THE, the army, RMY, is IS, coming, 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 be out. Then, in fact, I wanted to write be outside, but I didn't have space, but then I stopped here. It's fine. So this is what I wrote. The army is coming, be out. And then I unwrapped the paper from the cylinder, and of course it's very long, so I cut into 3 pieces and I took a picture for you, and this is what you now try to read. It's very funny. It's TRSIEHM. You don't see the army is coming, be out anymore. So this is a little bit advanced. This is using we are permuting the letters in the plain text. Okay, fine. So now, of course, I cannot continue my historical review because it's full of events. The Caesar cipher is very important. He moved by 3 positions the Latin alphabet. Caesar, the famous Roman Caesar in Rome. Another important date, 800 AD, an Arab I think this was in Iraq or Baghdad probably. Abu Yusuf Ali, he invented the frequency analysis to break, for example, the Caesar cipher. The Vernam in 1917, it was suggested by a US general so this is like an improvement of Caesar cipher. And then the Vernam is more or less used in the Enigma. Here I mentioned also the machine. So the Enigma was used by the German army during the Second World War. Lawrence was used by the German administration, but it's more or less the same technique. Okay. And then you have something very famous also in the 70s called DES. But it was nowadays, it was replaced since almost 2 decades by the AES. And I'm to show you the AES in my talk, not the sensor. I will show you the AES. Okay. So let's say, quickly speaking, cryptography can be more or less divided into, besides post-quantum, the modern cryptography before, it can be divided into asymmetric and symmetric cryptography. So as you see on the top of my slide, we'll introduce asymmetric cryptography, then I will talk about symmetric cryptography. So the AES is part of the symmetric encryption, symmetric cryptography. Okay, so when modern cryptography, I mentioned the word, this type of modern cryptography started, it started in 1976. So before 1976, what did we have? Nothing besides the paper of 49 I mentioned by Claude Shannon, but nothing important really in cryptography. And what Diffie-Hellman did, in fact, they were not only Diffie and Hellman, a guy is hidden behind also. The third guy is called Ralph Merkel, but for some reasons, people, when they call the protocol, they don't say Hellman Merkel, they say Diffie-Hellman only, but it should be called Diffie-Hellman Merkel because he worked as much as them in making this protocol. I will show you this protocol now in my next slides immediately. So this was invented in 1976, and this is really a breakthrough. And following the Diffie-Hellman protocol for key exchange, we have the RSA in 1977. Why RSA? Because these are the authors also, like DH for Diffie-Hellman. So Ron Rivest and Adi Shamir and Leonard Adler. Okay, so this is for encryption. And 1985, ElGamal was a student of Martin Hellman. He modified the Diffie-Hellman to make another type of encryption, very, very interesting also. And finally, I'm giving another important date, 1985, like more or less the foundation of elliptic curve cryptography. Okay, let me show you Diffie-Hellman, the one of 1966, and you will see. So it's based on prime numbers. Everything is in numbers in cryptography. We need numbers, otherwise it doesn't work. So I will just recall what is a prime number. A prime number, this is a number which is only divisible by 1 and by itself. Okay, so if I take numbers which are not prime, 4 for example, 4 is 2 times 2. 4 be divided by 2. 6 is 2 times 3 divided by 2 and 3. 8 is 2 times 2 times 2. 9 is times 3. 10 is 2 times 5, and so on. So these numbers are not prime. So the first I'm giving are prime numbers, 2, 3, 5, 7, 11, 13, 17. Fine, but you're not going to use the small numbers. If you use small numbers, not even a computer, someone using a small calculators, even using your pen, you can break the cryptography if you use small numbers. You need big numbers to make things difficult in cryptography because we don't want Eve to be able to find the plain text from the ciphertext. So the question is, can we find large prime numbers? Yes, if we use simply something called Bertrand postulate, or we can also call it the Bertrand lemma. So this was conjectured by Joseph Bertrand in the 19th century. Between two numbers n and 2n, when n is, in fact, this is true for any n, but mainly when n is large. This is what's interesting us. There is at least one prime number. Now, of course, if we use for people who knows more about prime number, for example, use the prime number theorem, you know that between n and 2n, when n is large, you have almost n over log n. So you have a lot of prime numbers, in fact, n over log n. But there is at least one. This is the Bertrand lemma. And here I'm giving you some big prime numbers. 400,000, sorry, 40,099. And then the last number, I cannot read it. This is 599 and something like this, 66519. Of course, you may say, but how do you play with these numbers? How do you manipulate these numbers? How do you create these? You need a number theory software. You cannot do it by hand. You need the number theory software. The standard languages like C, C++ cannot handle, not even Java cannot handle these numbers. Now you may say maybe in Python, sometimes the number will be so big, even the P in Python will not be able to handle them, or it will be very, very slow if you do Python. So I'm using special softwares in number theory. I'm not using any. So let me show you the Diffie-Hellman protocol. And you will see it's not very complicated. Huh? In a couple of slides, you will understand what's happening. So we have Alice and we have Bob. And before, of course, before sending a message, encrypting the message and sending it to Bob, we need, remember, with secret key, we need something to be shared between Alice and Bob. Now, of course, imagine Alice and Bob were brother and sister, they grew up together, and then they know a secret, and then later, 20 years later, they can use that secret. But no. Here I am. My question is, Alice doesn't know Bob at all. Alice didn't talk to Bob before. This is the first time Alice is talking to Bob. You may say, what? How can Alice and Bob share a secret? This is the first time. Yes, this is the first time. And Eve is here. And Eve is listening. So Eve is listening to anything. Anything going from Alice to Bob, Eve is getting it. Anything going from Bob to Alice, Eve is getting it. But how can we transmit? How can we exchange a secret? Let me show you. Okay. So the magic of Diffie-Hellman, it's a very nice protocol. So of course, what can be Alice in practice? It can be a machine, a desktop, a laptop, a tablet, a smartphone. What is Bob? It can be a server, but it can be also another machine. Maybe one machine is talking to another machine, not necessarily a server. It can be a peer-to-peer communication, not necessarily using a server. So, but of course, for simplicity, I'm not going to talk about machine, desktop, laptop. I'm talking about Alice and Bob. Okay, so what do we do first? First, to start the key exchange, we select a prime number, P. Wait, guys, look at this prime numbers. So I did it on purpose. I put a very big prime number to show you it's a really big prime number. So how many decimal digits? 308, who cares about the 8? It's about 300 decimal digits. If you write this number P in binary, you get 1024 bits, or about 1024 bits. So this is huge enough. And alpha, this is another number, very small, let's say 41. And we assume that P and alpha are known. Everyone knows P and alpha, even the spy. So we on the radio, on TV, on social media, on the internet, everywhere. This is P, this is alpha. Everyone knows P and alpha. Public. These are public numbers. Now we will start with the secret numbers, with the private numbers. Okay, so what Alice is going to do, Alice is going to pick a random integer, A. A is secret. Okay, and this is the A. And this is the A I did for you in this talk. So I took a random integer. It's also about 1024 bits, big enough. And notice only Alice knows A, not Bob. No one knows A. Small a. No one knows A. Fine. Now, Alice is going to compute. Remember that alpha and P are public. Alice is going to compute big A. What is big A? It's alpha raised to small a modulo P. All operations are modulo P. Fine. So this is big A. How did we get this big A? It's alpha 41 raised to the small a I showed you before, modulo this P. Fine, and we get this big A. And now big A is transmitted on the public channel to Bob. Everyone knows big A. Of course, because Alice is using a public channel, and Eve is getting also, the spy is getting big A. Everyone knows big A. But only Alice knows small a. Now this is on Alice's side. We do the same on Bob's side. Bob will pick up a random integer small b. Small b is about 1024 binary digits, which is about 300 decimal digits, as I said. Only Bob knows small b. Only Bob knows small b. And Bob will do this same. Big B is alpha raised to small b modulo p, and big B is transmitted back on the public channel. That's why if you look at my picture, I put the arrows, I put doubles. So this is like, we call it in telecommunication duplex channel. It means Bob can talk to Alice, Alice can talk to Bob. Okay, so Bob transmitted back B, and big B is alpha raised to small b. Everyone knows big B. Fine. So Eve also knows big A, big B. Now, how do we get the secret? The common secret of Alice and Bob, a common secret that Eve cannot get. Very simple. Alice is receiving big B, sorry, and it will do big B raised to small a, because Alice knows small a. And what is this? This is alpha raised to B raised to A, so this is alpha raised to AB. Bob will do the same. Bob is receiving big A. He's a small b. Will do big A to small b. But big A is raised to small a, so this is alpha raised to AB. Well, wonderful. They get the same number. And I'm showing you the same number. So S is 6596, whatever, ending with 7031. So this is the secret shared by Alice and Bob. No one can get the secret. Why? Because if you want to get the secret, you need small a or small b. You cannot get small a from big A. It's very complicated. You cannot get small b from big B. It's very complicated. The task may take you thousands of years. And we can do things such that the task will take you, not thousands of, take you billions of centuries of centuries. It will never finish. So this is possible also. It depends on the size of these numbers. How big are these numbers? Okay. So in my simple demo, let me summarize what I did in my simple demo here. Alice selects a secret small a. It sends alpha to A to Bob, modulo P. Bob does the same, small b, and big B is alpha to B, sends to Alice. And then we do B to A and A to B, and we get alpha raised to AB. Only Alice and Bob can get secret, no one else can get it, and all operations are made modulo this number, which is also public. Okay, so this was, I mean, when you see the algorithm now, it seems very simple. It's alpha raised to AB, it's very simple. But before 1976, no one suggested a key exchange algorithm, okay? Now, what I showed you in my demo, 1024 bits, this can be broken using current technology. No. Now, where is current technology? I put some records for you. So for solving the discrete logarithm, what is discrete logarithm? I give you alpha raised to A modulo P, you have to find A. You cannot apply the log to find A. Why? Because this is modulo P. Of course, if there is no modulo open, if just I give you alpha raised to A, you apply the log base alpha, and then you get A directly. But you cannot do it because of the modulo P. So this is called discrete logarithm. This is a special logarithm modulo P. And up to now, it's a French team who did the best in December 2019. It's 795 bits, but you wait, it's almost 100 bits, and this is very close to 1,000. Yes, it's not recommended nowadays to do 1,000, go up to 4,000, but I can tell you, going from 800 to 1,000, we still have just 200 bits and something to break 1020. It's very difficult. It's very difficult because the current technology, it's not fast enough. Computers are not fast enough, despite, if you look at the tables I put below, the most powerful supercomputer in the world. This is from June 2020, last month. It's a Japanese computer. It can do, you can read the Rmax, it can do 415 petaflops, so because it's 1,000 times teraflops. Flops means floating point operation per second. This is huge, and it has almost, I mean, a little bit more than 7 million cores. Okay. Now the number, of course, is not necessarily the linear in the Armax, or Armax not linear in number, of course. Look at the power consumption. So this is the power consumption in kilowatt. Just to give you an example, one is one iron almost. Okay. So you need to put at home. You put on, switch on 28,000 irons. So this is 28 megawatt of power consumption to get this computer. And even this computer nowadays cannot break the example I gave you, 1024 bits. Sorry. For integer factorization of integer, this is for RSA, more or less the same, 800 bits, and the record date back to February 2020 with the same team. The same team are working on both records. Okay. Now, I would like to show you the RSA, or symmetric encryption. So to understand what is asymmetric encryption, I will show you again two pictures side by side. So on the top, you see what we call a symmetric crypto system, symmetric key system. Alice is using key 1 to encrypt. So the message, the plain text, is becoming a ciphertext. And then Bob is using the same key, key 1. This is very similar to my first picture I showed in my talk, and key 1 is used to decrypt. So you can see key 1 on both sides. So that's why we call this symmetric cryptography. Now, let's look at the system below. Completely different here. We have key 1 to encrypt. What does it mean, public key? So it means Alice wants to send a message to Bob. Bob published somewhere a public key. It can be on the internet. It can be on Bob's website. It can be Bob gives to Google the authority to publish on his behalf. This is the public key of Bob. And then I ask Google, please give me the public key of Bob. And then I get the public key of Bob. And it's called key 1. So key 1 is known by everyone. Anyone on planet Earth who would like to send a message to Bob will use the public key of Bob. And then we send the message to Bob. But no one else encrypt. No Eve. Eve in the middle, Eve will get the ciphertext. Why? Because in order to decrypt, you need the private key. And who is the only owner of the Bob? So the private key, key number 2, is only possessed by Bob, and only Bob can decrypt. So you can see that's why it's called asymmetric, because we use two different keys. One for encryption, one for decryption. The one for encryption is the public key. Yes, because many people can send messages to Bob. Now you can have Alice 1, Alice 2, Alice 3, and so on. You can have many Alices, but you have a unique Bob. One guy who's going encrypt, so you should have the private key, the decryption in this case. Okay, again, compared to the system above, key 1, this is symmetric key encryption. Okay, but unfortunately, I will show you later that the symmetric key encryption is much faster than asymmetric. So we cannot use asymmetric when you need high throughputs in digital systems. Okay, so now look what I do in my pictures below. It's very weird. I don't know if you see, I switch the private key and the public key. Okay, so this is the initial system, encrypt, decrypt. Now I'm going to give the private key to Alice, the public key to Bob. Means now only Alice can sign a document, and Bob can check that this document was signed by Alice. So now I'm converting the asymmetric key system, asymmetric encryption, into digital signature. So we are doing now digital signature with the same system, but we flipped the keys. We put the private key on Alice's side. So Alice is the only person who can sign the document. And then now you will have many Bobs. You will have Bob 1, Bob 2, Bob 3. Any of those Bobs can do what? Can take the public key of Alice, and then he can verify that this document was really signed, was really written by Alice. So this is a way of creating an electronic notary, because when you sign an agreement in real life, usually you go to the notary and the notary will put his stamp. But in electronic transactions, the notary is not there to put a stamp. You need an electronic stamp, and this is the electronic stamp. So this is, you can call it the electronic notary, the digital signature, okay? Symmetric key encryption cannot do digital signature. Only asymmetric can do. You just flip the private key and the public key. There is no private key, public key in this key encryption. It's only a private key, secret key, shared by both of them. Okay, so let's see what is RSA. It's a key generation. You choose two large numbers, P and Q. They are private, they are secret. You don't publish them. What you publish the product, N equal P times Q. And then you compute lambda equal, you can take lowest common multiple. You can also take P minus 1 times Q minus 1. It also can work. So you get this lambda, but lambda is not published. Lambda is, you keep it private. And then you publish a number called E. E not very large in practice, but you have to choose E. Such E and lambda are co-prime. And as I wrote here, E is public. And then you find the inverse of E modulo lambda. The inverse means D times E is 1 modulo lambda. So this can be computed very easily using Bezout ID. So once you have the D, you keep the D as private. So let me summarize very quickly. The public keys to do the RSA, to do asymmetric encryption, which also can be converted into digital signature by flipping the keys. So how do I generate the keys? I have N public, E public. What is private? P times Q to build N. So that's why if you are capable of factoring N, you break RSA. So you need to factorize very, very large numbers. And this is not easy in practice. Okay. Now, P and Q are private, lambda is private, but the most important between these secret keys is D. Why? Because I'm going to use D for decryption. Of course, the private key should be used for decryption. That's why it's D. And guess E. E is for encryption. Okay? And this is how it works. So Bob will send his public key NE to Alice. Alice has a message M to send Bob. Alice will do the following. M raised to E modulo N. The message raised to E modulo N. You get the ciphertext. You send the ciphertext to Bob. Bob will do what? Bob has private key D. Bob will D raised to D. Magic, you get M. Now, the proof is not very complicated. You need the Fermat-Little theorem and the Chinese remainder theorem, and then you get the proof. It's not very complicated. It takes a couple of 2-3 pages to write it down, and then, or 1 page if you write it compact, can get the proof. So C raised to D gives you M back, which is wonderful. Now, of course, who can decrypt? If the spy tries to decrypt, need D, but D is private. Only Bob knows D, and D is a big number. It's a very big number. You cannot get D easily. Now, of course, if I go back to the key generation, if you are capable of factorizing the public number N into times Q, you can get D because you have E. You just need to find the inverse of E. D times E equal to 1 modulo lambda. And this is very easy if I give you P and Q. Of course, P and Q are also given, are hidden, are not given to Alice. So Alice needs just E and N. Alice will do M raised to E modulo N, and she gets the ciphertext and send the ciphertext on a public channel to Bob. Now, remember, I flipped D and E to get the digital signature. Very simple. Okay, so I have some signature S. I do S to D, I get C. I give C to Bob, and Bob can check very easily. How? By doing C raised to E, and he will get S again. So by flipping, remember, this is very nice in asymmetric cryptography. You flip the private key and the public key, you get signature. Okay? So this was invented after Diffie-Hellman. And of course, this is part of what we call modern cryptography. And then later in 1984, ElGamal invented very nice encryption also based on Diffie-Hellman. Modification of Diffie-Hellman. I'm using the same notation. How do you do encryption? C is equal to M times alpha raised to AB. Of course, because alpha raised to AB is a shared secret between Alice and Bob if we do the equivalent of Diffie-Hellman. And then how do I decrypt? I just need to invert alpha raised to AB. So here I have alpha raised to minus AB. What does it mean? This is the inverse modulo P. Of course, if P is prime, this is an inverse in a field, but you can do ElGamal in a group, and then you have to find the inverse in a group. It's the same idea, the same algorithm. Usually practice, they use numbers and fields. Fields are easier to deal with rather than groups. Okay. Now, otherwise, if you are forced to use a group somewhere, you can do the group and invert in the group. Okay. And so the ElGamal encryption, the difference between RSA and ElGamal is that if Alice changes A, Alice can change A at each encryption. Then you get some randomness in the ciphertext because it will have alpha to A, and the small a will change C also. So for the same message M, you have more randomness in the ciphertext. So some people call this probabilistic encryption because it has more randomness than RSA. Okay, in RSA, if you put the same message, the same key, you get the same ciphertext. The same for AES, for symmetric encryption. Okay, so finally, as I said, how can we break this in cryptography? This modern cryptography is based on the hardness of computing discrete logarithm or the hardness of factoring integers for the RSA, for example. Now, these problems, discrete logarithm or factoring integers, cannot be solved easily using standard computers. However, if you have a quantum computer, since the 90s, since 1996, there is an algorithm proposed by Peter Shor, and this algorithm can factorize numbers, and the same for discrete logarithm, in polynomial times. So it means if we are capable of building a stable, because right now, all of them are trying to build a quantum computer, but it's not built stable yet. We may wait 20 more years to have a stable quantum computer. So, but let's say if this computer comes, it will kill integer factorization and discrete logarithm. So it means in the future, we need to change all these encryption algorithm and do something which is post-quantum. Post-quantum means it should resist to quantum computers, to algorithm running on quantum computers. Okay. Now I'm switching to my last thing before the conclusions because time is running out also. So let me show you a little bit symmetric encryption, how symmetric encryption is working with a very famous algorithm called AES, Advanced Encryption Standard. This was invented by two Belgian cryptographers in Leuven in Belgium, Damon and Raymond. And it's also called Rendial. The IJN, it's pronounced Rendial. So it came in the USA in 2001, 3 years later. It's really a very efficient algorithm. So this is now almost 2 decades ago, a little bit more. It can run very, very fast, believe me. Much faster than ElGamal, much faster than Diffie-Hellman, much faster than RSA. So when you implement the AES, which is symmetric encryption, it can run sometimes 1,000, 10,000 faster than asymmetric cryptography. And we need speed. We need speed in new systems, of course. Now, I made a list showing you how important is AES. So this is really, these are major applications of AES. Point-to-point web connections. Each time you do HTTPS, HTTPS is using TLS, and TLS is using AES. WhatsApp is using AES because it's using Signal. Facebook Messenger is using AES. IPsec is a protocol used by VPNs, by virtual private network. It's also using AES. If you take processors by Intel, by Apple, inside these microprocessors, you have doing the AES in hardware. And this is only nowadays on our smartphones. So you can run the AES, you don't need to write a function in software. You can just ask the CPU will do AES for you very, very fast. This is very fast. Okay, so the AES works like this. It takes blocks of 128 bits and it generates blocks of 128 bits. And for the key, you have 3 different key lengths. You have 128 bits, 192, 256. But I would say nowadays you should take only AES 256. Why? Because as today, as announced in my last bullet, all possible attacks on the AES did not succeed. Fine. So it means in 2020, AES is used everywhere. We don't know any attack that can break AES. Okay, fine. But guess what, guys? We don't have a proof of security. So AES was invented in 1998. And at that time, people were not asking for a proof of security. Nowadays, if you try to submit to make a new standard, something like AES, this will be rejected by the community immediately. No way. In 2020, we cannot work like 98. Why? Because cybersecurity and cryptography in 2020, they become much more important than 20 years ago. So nowadays, if you suggest an algorithm, an encryption without a proof of security, reject it immediately. What can we do with AES? It's here. We don't know any attack that can succeed. We keep it. But again, we don't know. Maybe if in 20 years it's broken, it's broken. It's a disaster. Okay. So probably people will change it soon, and it will not stay the standard. Okay. So this is how AES is working. It's a network of substitution of permutation. I'm showing you many functions of AES. You take a plain text of 128 bits. You add a round key. You do substitution of bytes. You shift rows. You mix columns. You add a round key, and then you start a second round. And each time you do a round is an iteration. You change the key. Amazing. You may say, but wait, how can I get many keys? I have one key. I have one password. I don't have many passwords. Of course, we're going to create many keys from out of this key. But let me just comment about this last bullet here, the second one. Something called very difficult to pronounce, Kerckhoffs's principle, 1883, and reformulated by Shannon as the enemy knows the system, meaning the AES is secure not because you are hiding. No. You can know what AES is doing. Everything's published. We know bit by bit what the AES is doing. AES is secure just because you put a key and the key is secret. And that's why it's secure. So a crypto system should be secure even if everything about the system except the key is public knowledge. And this is what the AES is satisfied. Now, the 2 other properties I mentioned before, 45 minutes ago, confusion and diffusion. Confusion, we don't know. We don't want to find the key from the ciphertext. So a binary digit ciphertext should be connected to many parts of the key. So this is called confusion. You confuse the spy. You don't want the spy by getting the ciphertext to guess the key. But also you don't want this by getting the ciphertext to get the plain text. So this is the diffusion property. If you change 1 bit in the message, it will change almost 50% of the bits of the ciphertext. And these confusion and diffusion properties, they are really satisfied by the implementation of AES, how it was done in 98, how it was designed. Okay, quickly speaking, guys, AES is a block cipher. It means it works block by block. It takes a plain text of 128 bits. It generates a cipher of 128 bits. How do I write 128 bits? I write them as a matrix 4 times 4, and each entry is a byte. So you get 16 bytes. Now, if you count 16 bytes times 8 bit by bytes, you get 128 bit. So this is called the state. And then all operations are made modulo this polynomial. This is an irreducible polynomial. We call it the Rendile polynomial. It generates a Galois field, the finite fields of size 256. So when you take a byte is 8 bits, 8 binary digits. You will see the byte as an element of the finite field. You can write it as a polynomial of degree up to 7, not more than 7. And then when you add multiply polynomial, you take modulo this irreducible polynomial. So this is very simple. This is like Galois theory applied to cryptography. We use this in the S box, in the subbytes. This is the nonlinear part of AES, okay? So this is the round, what I put here. This is one round. And when we take 256 bits in the key, we do 14 rounds. We repeat this block 14 times, okay? So the add round key, as I mentioned before, we take the original key and we generate many, many keys, 1 key per round. So if you have 14 rounds plus the initial round, you have to generate 15 keys from the initial. How? One, we do cyclic rotation of the 4 bytes in the column. We do substitutions of the bytes using something called the S box. We add the 32-bit constant. So this is like XOR. And then again, we XOR with the previous first column of the previous key. So I'm not showing the picture. I'm just explaining quickly. The picture can be found on Google. It's very complicated how the keys are generated, but once you understand the pictures, the design of the key exchange, the key schedule, it's very simple. Okay. So remember, from 1 key we generate many, many keys. Why this is important? This is the confusion. This is the confusion property suggested by Claude Shannon. Now the S box. The S box, it takes 1 byte. It does this weird, what we call affine transformation on the byte. Okay, so first we take the input of the S box, we invert in the finite field, and then we apply the affine transformation. The affine transformation can be written like this. You take the byte, you shift 0 times, XOR with itself, you shift once, XOR with itself, and so on. And then at the end, you add this constant. This is a constant which was chosen by the standard. So the S box is doing what? Is taking 1 byte at the input, modifying by, this is very similar to the Caesar cipher, almost 2,000 years ago. The Caesar cipher 2,000 years ago was doing substitution. The Atbash by the Hebrew 2005, it was doing the same function, but here we are doing it on bits. We are using the nonlinearity coming from a finite field, okay? And finally, the shift rows and mixed columns, they do also operations on the bytes to do what? To do the diffusion property in AES, okay? So it's, and I cannot say more because it will take a lot of time to, so for example, my students in Qatar, 2 weeks ago, they had the project, they had to write all this algorithm in C language and then run it in a lab session. We gave them 2 weeks to understand the algorithm and then to implement in C language. So I do my best, but I don't have 2 weeks in this talk to show you all the details and run it in C language in real time. Okay. Now, how do we use AES? AES is used everywhere, as I showed you before, but the problem is the key exchange. And if you don't have a secret key, you cannot do AES. How we are doing the key exchange? Using Diffie-Hellman, using RSA, or using ElGamal. So in fact, finally, the asymmetric cryptography is used to exchange secret keys. And then the true cryptography, the true encryption, is based on AES because AES runs very fast. Okay. Now, I will not talk about something, but you can go and read in books something called stream ciphers. One of them is very important, very recent, called ChaCha 20, and ChaCha 20 is competing with AES. And of course, something called hash functions. I didn't about hash functions in this talk. You can do hash functions in a tree. This is called Merkle tree, and this gives you the blockchain. And the blockchain is used in cryptocurrency like the Bitcoin. Okay, so let me show you this nice table. TLS for secure web is using AES or ChaCha 20, and for the key exchange we use Diffie-Hellman or elliptic curve Diffie-Hellman, another version of Diffie-Hellman. IPsec for virtual private network, and IPsec is competing with WireGuard. WireGuard is a new protocol for virtual private network, but you have people pro, it depends. I don't know. I'm not against, I'm not pro. They say that ChaCha20 is faster than AES. It's not true because ChaCha20 is not implemented in the CPU, AES is in the CTU. And finally, I put in the table the Signal protocol, a protocol called Signal used by WhatsApp, Facebook, and since 2 years by Skype. Skype is owned by Microsoft. Microsoft decided in 2018 to use Signal. And Signal uses only AES and elliptic cryptography, elliptic curves, Diffie-Hellman key exchange protocol. Okay. Now, a quick word before showing you my conclusions about post-quantum cryptography. What is a quantum computer? A quantum computer is a computer that uses physical phenomena such as superposition of states, of quantum states, or entanglement of quantum state to do computation. So the picture you see here, this is a quantum computer by Google, I think, if I'm not wrong. They have many of them, Google. They have at least five or eight quantum computers. It's very expensive to build such a computer. It takes time. It's not very stable. Right now, they are recently, I was reading a paper, they were very happy by just factorizing 15 in 3 times 5. Fine, so we are very far from factorizing 1024 bips by a quantum computer right now. Okay, so however, quantum computers, if they exist, if one day they are stable and we can run a quantum algorithm, they are able to solve computational problems much faster than classical computers, mainly factorizing integers, okay? And what is post-quantum cryptography? It's a cryptography that cannot be broken by quantum computers. And the most important one is the one based on lattices, one based on hash functions, that is on codes, on error codes. This is called McAleese-like cryptography. But I think most of the work is creating on lattice cryptography, mainly something called LWE, learning with errors, and probably the next start for post-quantum cryptography will be based on LWE, on learning with errors. Okay, so my conclusions are: asymmetric cryptography provides key exchange and digital signature, which is very important. This is the electronic notary. Now, of course, you can do, if you would like, encryption using asymmetric cryptography, but it's very slow. It's not recommended. How do you do encryption using symmetric cryptography? It's fast and secure. Now, both are needed in almost all systems now, of course. So what can we say? Military, governmental institution, and the industry, they have a lot of tools for cryptography, no problem. What you remember from my talk is the last bullet. The last bullet, we as individuals in 2020, in year 2020, we have at our disposal a variety of tools for encryption. Now you may say, why? Privacy, confidentiality, mainly because all governments are doing mass surveillance, whether they are democratic or non-democratic. Forget, all of them are doing surveillance, and you have also attacks by cyber hackers. You want to protect also yourself against cyber attacks. And this is new. If you go back 20, 30 years ago, the individuals didn't have enough tools for cryptography, not like nowadays. So my important conclusion, I would say, is the last bullet. Thank you very much.
Thank you very, very much, Joseph, for this very interesting presentation. And I know that Veronica has collected some questions for you. So yes. Veronica, could you please ask the questions we have for Dr. Boutrous?
Yes, I'm open also the chat. I think you wrote the questions. Yes. Veronica, you can read the first question. Please go.
Okay. We thank Juan Pablo for his question. He says he just finished reading Simon Singh's book, The Code, and was left with this question. In your opinion, Professor Boutrous, what will happen first? Computers will be able to resolve the RSA one-way function issue, the prime factorization, or the fulfillment of quantum cryptography?
Yeah, Okay, thanks for the question. Interesting question. So, but careful, there is no quantum, it's post-quantum cryptography. The post-quantum cryptography can run on a standard computer. You don't need a quantum computer to run post-quantum cryptography. You can run it on any computer you have right now. But what is nice is that a quantum computer cannot break the post-quantum cryptography running on the standard computer, on a classical computer. Amazing. Okay. Yeah, so you should say post-quantum, not a quantum cryptography. So your opinion, what is first? Can we resolve the one, the RSA is not a one-way function. Let's say if we factorize the integer n in RSA, we break the RSA. So it's a question of integer factorization. Good question. Okay, again, what can I say? I showed you that in integer factorization, we are blocked at 800 bits nowadays. Are we going to reach 1000 or 4000 bits before the fulfillment of a quantum computer, let's say, not quantum cryptography? Difficult question. I would say they finish probably building the quantum computer before that we break it using standard algorithm. Yes. So let me be optimistic. I mean, Google is putting a lot of resources. IBM is putting a lot of resources. Microsoft already built the whole software. So Microsoft, they have an entire operating system that can run on a quantum computer, but the hardware is not there. So the software is ready, the hardware is not ready. I believe, given the resources put by Google and other companies, probably we will have the hardware of the quantum computer before being able to resolve the RSA one-way function using standard computers. So I am for the second part of your question. Yes, for the second part. But who knows? Maybe I'll be wrong in the future. We will see. Yeah, Veronica, please, the second question.
Okay, we thank Joel for the second question. And he says each encryption method was good until they were broken. You have said that in 20 years, the current methods probably are going to be obsolete with quantum computers. In your opinion, how many years will we need to develop new, secure, or robust encryption methods?
Very interesting question. So the answer is 0 years, because we have them already. We have already post-quantum encryption methods, but why we are not using them? Because you cannot put in public a new algorithm without having a standard. A standard means you need to think that all companies are using the same standard. Otherwise, Microsoft will have its own encryption, Google will have, Amazon will have, Facebook. No, you need all these companies to have one standard. And the standard will be soon, 1 or 2 years. But from algorithm point of view, we have dozens of algorithms which are already resistant to quantum computers. So no worry for that. We are ready. We are ready for the quantum computer. Okay. So please, Veronica, the third question.
Okay, the third question is from Gustavo. Thank you very much. I wonder if there was a case in which certain crypto algorithms in some specific cases were broken using brute force with some accelerator based, as examples, GPU or TPU infrastructure, which, if he understands well, is receiving an increasing attention nowadays because of their computational power, or rather if it's still not a concern to be worried about even using this kind of technology?
Very good question. So yeah, indeed, what we have since, now the TPUs are recent, more recent than GPU, but let's say the GPU appeared in 10, 20 to 12, sorry, 12, no, 20 years ago, we didn't have GPU yet, but let's say 12 years ago, thanks to NVIDIA. And then we noticed that GPUs can do parallel computation, and then we start them in parallel computations to accelerate. TPU are by Google only, but you can have access to TPUs through Google. TPU, they run very fast, but don't have enough accuracy. So they are mainly for machine learning, for training neural networks. But now imagine you put GPUs, TPUs, you put a large number of GPUs and TPUs. You can you even use all the supercomputers I showed you, if you remember. This is nothing. Why it's nothing? Because the problem is the complexity if you do a brute force, because your question is about a brute force approach. Brute force, if I use 1024 bits, this is around 300 decimal digits. This is 10 raised to 300. Try it. Imagine you can do one operation in 1 nanosecond. Okay, 10 raised to 300, 1 nanosecond. This is nothing. You are taking out 9. Okay, imagine you are very fast. You do one operation in 1 picosecond. Okay, fine. Take out the 15. You have 300. And if you convert this into seconds and then minutes, and you will find yourself sometimes with billions of years. And remember that the age of the universe is 15 billion years, 13, more or less, 13 billion years. So you're going to exceed the age of the universe. So my answer is GPUs, TPUs, when you use a large number of bits, cannot help the brute approach. No, unfortunately. Yeah, force a question, Veronica, please.
Okay, we have one more. Thank you, Enzo, for this question. Professor Boutros, if the asymmetric key encrypt, knowing that the encryption code or key is public, doesn't mean that everyone can see the message before it's encrypted.
No, because the message is owned by Alice. Alice is the sender, okay? Alice is not supposed to put on the public channel the plain text. Alice will take the plain text, it will read the public key of Bob, encrypt the plain text. Now the plain text becomes ciphertext. Alice will put public the ciphertext. So no. So the answer to this question is no, there is no risk in this case. The public key is for encryption. Why? Because to allow any person to encrypt and send to Bob, and Bob has the private key to decrypt. Only Bob has the private crypt. And when you send a message, you never send the plain text, of course. Otherwise, people read the plain text. You send the ciphertext encryption via the public Bob. Okay? So thank you, Veronica. If there is any other question, please do not hesitate. And remember, I showed also at the end, let me get rid of this window. Yeah, I showed you 2 excellent references in cryptography. If you like mathematics, you can take this book of 2014. It's Introduction to Mathematical Cryptography. And then it's more engineering approach, the second book, Introduction to Modern, but them are nice books. Of course, the second one will cover more cryptography than the first one, but I like both. Okay.
I have a couple of questions on my
Yes.
own.
Yes.
The first, from a kind of user standpoint. So if you take, for example, WhatsApp and Facebook Messenger, as you pointed out, they are end-to-end encryption, and they kind of boast, they are proud that they are end-to-end encryption. And if it's not end-to-end encryption, what is it, and why is it worse than end-to-end
so this
encryption?
is the problem that arises recently with Zoom. We are using Zoom, but we right now everything is public. We have nothing to hide. So if someone would like to, if Eve would like to spy on us, it's fine. The spy is welcome. What happened in Zoom? So now you will understand what is the difference between end-to-end. So Zoom was doing the following. The encryption was between the user and the server by Zoom, and then between the server and the other end. So it means that a Zoom server owned by the company was capable of encrypting or decrypting the communication. This is not why it's not okay. Because if you are administrator at the company, even if you swear to the boss of the company, no, I will. Someone can tell you, okay, guy, look, Marcelo, I will send you $1 million on a private account in Switzerland. You work at Zoom. Please, I would like you to use, the private keys of Zoom. I would like you to decrypt this communication at the server level, and then get me what they are saying, and you will do it for me. Remember the human weakness. So what I forgot to say in this talk, sorry guys, cryptography is the child of is generated by mathematics. We do mathematics in cryptography. We can do cryptography almost unbroken. I mean, it depends on the computer trying to break the cryptography. But there is something which is much weaker than cryptography: the human being. So I give you money, and then you, as administrator, you will read at this the Zoom node. You can read the communications and you can decrypt them. This is not happening with WhatsApp. When we say end-to-end, it means if I call you Marcelo using WhatsApp, my WhatsApp application will encrypt in my phone. Who's decrypting? Your WhatsApp application on the other side, end-to-end. So of course, our data packets will go through WhatsApp servers, but WhatsApp servers cannot decrypt what we are telling, what you are telling me and I'm telling you. They cannot decrypt the communication. Okay, Zoom, they were capable of decrypting. Plus, not only that, of course, this didn't make United States very happy. They noticed that some servers of Zoom were located in China, and some of the servers were storing keys, encryption and decryption keys. Wow. And of course, the Americans said, what? Some Zoom servers are in China, and so they get very mad, of course. Yeah. Okay, is it fine, Marcelo? Yes,
it is. Okay. Thank you. It answered my question. Then I have another one, which also from the user's standpoint. So when I go to, say, a website to do some online shopping, for example, is there a way in which I, as a user, can know what shop uses a more secure encryption? So if you're in the internet, you put HTTP and then you get into Amazon or you get elsewhere, and you send your data, but are there shops that are, say, safer than others? How can I know?
Yes, because the standard is moving with time. And what I put here, you can see on the top of this slide, good question, Marcelo, you can see TLS 1.3. So what do you expect if I write TLS 1.3? So before 1.3, we had TLS 1.2, and before TLS 1.2, we have TLS 1.1. And guess what? For TLS, we have the answer of TLS, SSL. Now, SSL is weak. It can be broken. So it means when you do HTTPS, if the website is old and using SSL, now I imagine, for example, Firefox will not accept. I didn't try, but I'm sure Firefox will not accept. Why? Because Firefox, they drop SSL. Now, I cannot say about other web browsers. So this is like a protection should be in the web browser should refuse to use old versions of TLS. Now, the best version is the new one, TLS 1.3. It's excellent. It uses AES 256 and SHA-20, and the key exchange is based on Diffie-Hellman, and not any Diffie-Hellman. They changed the key. So the key is ephemeral, means in the future, if it's recording what you did now, in the future, he cannot decrypt in the future. Okay, so TLS 1.3 is very secure. Now, I'm not saying that TLS 1.2 is not. So TLS is under, Marcelo, is under HTTPS. You see what I mean? You do HTTPS / your bank address. So HTTPS is calling TLS, of course. And so we hope that your TLS, now, can you know which TLS your web browsing and the other, there is a way to know, but usually the user is knowing every time to check which TLS you are using. But I mean, nowadays we assume that TLS is fine, but you should stop using SSL, the ancestor of TLS, the old DPS.
So if I understood right, then a lot of protection comes from the browser you use, right? And if this is the browser, case, what browser would you recommend?
For security, Firefox is the best. Now, if you want a browser checking into your computer without your authorization and reading your files and doing all spying, you take a Chrome. Chrome is the best spy to spy on you by Google. This is what I can say. Sorry. I mean, some people may not accept, but you can go and see on Google. So cyber experts do not recommend cyber experts. I'm not really a cyber expert, but I know some cyber security. Do not recommend Chrome. Firefox is the best for security. Safari, there is a new version by Safari, which very recent by Apple, is not so bad also, but I prefer Firefox personally. Yeah.
Okay. Veronica, is there any other question pending?
No, we have no more questions, Professor Garcia.
Okay, thank you. Thank you. Well, thank you very, very much, Joseph, for this very interesting presentation, for taking
Muchas gracias for listening to me.
taking time from your holidays and spending these moments with us. We're really grateful to you for that. Thank you for attending. Joseph, I will just switch to Spanish again.
Okay.
Just to
Thank
close.
you. See you soon. Huh? Bye-bye.
Bueno, muchas gracias por estar con nosotros esta tarde y yo aprovecho la oportunidad para mencionar que el 12 de agosto a las 18 horas, que es el horario tradicional de la charla, esta fue más temprano por la diferencia de horario con París, pero el 12 de agosto tendremos una charla que se intitula Fabricación Digital como herramienta de trabajo colaborativo y va a ser dictada por el ingeniero Mateo Acosta de Paraguay y por la profesora Gabriela Moholi de la Universidad Paraguay Alemana, nuestra UPA. Entonces, nos quedamos por acá en el día de hoy y hasta el día 12 de agosto a las 18 horas. Chao, saludos a todos.